After we had defined what is multiple correlation coefficient, recall that the setup we had taken was totally distribution free, and in a very general way we had defined what is multiple correlation coefficient. We have talked about its bounds and we have given one or two interpretation of it. Now, after that we had talked about in the case of a multivariate normal distribution, what extra interpretation can we give to this multiple correlation coefficient. So, in this sense we had considered the p-variate random vector, which was following a multivariate normal distribution with mean mu and dispersion matrix sigma. Of course, as we would partition x, we would have to partition mu and sigma. So, then mu was having one component here and the rest of the p minus 1 elements coming in mu 2, and similarly we had a sigma matrix partitioned in the form of sigma 1 1 sigma 1 2 vector, and then the p minus 1 ordered square matrix. And we had said that if I consider the conditional expectation of x1, let us, without loss of generality, we take x1 as the first random variable x1, so that I consider the conditional expectation of the first member of the partitioned vector and then conditioned on x2. And if you recall, this was nothing but mu 1 plus sigma 1 2. This is from our earlier results on multivariate normal, and this was then x2 minus mu 2, right. And what was the conditional variance? Variance of x1 given x2 was nothing but sigma 1 1 minus sigma 1 2 sigma 2 2 inverse and sigma 1 2, and we are giving a special notation to this and we are calling it sigma 1 1 dot 2 3 to p, right. And we had taken up the calculation of the correlation coefficient between x1 and this expectation of its conditional expectation conditioned on x2, the residual part of the random vector. And then we had seen that if I consider the numerator, that is x1 covariance between x1 and conditional expectation of x1 given x2, this was coming to be, we need to put a second bracket here, and this was covariance was simply sigma 1 2 prime sigma 2 2 inverse and sigma 1 2, and this fact led us to the fact that correlation coefficient, the one that we were interested in, was this correlation coefficient between x1 and the conditional expectation of x1 conditioned on x2 was nothing but, probably we had come up to this stage as well, because the variance of this is nothing but this factor. When we take the variance of this expectation, again we get back this type of the same factor. So, with the root of it, what we have is sigma 1 2 sigma 2 2 inverse sigma 1 2 with sigma 1 1 and raised to the square root. So, this is nothing but the usual multiple correlation coefficient, that is rho 1 dot 2 3 to p, so that I can say that rho square of rho 1 2 3 to p is nothing but sigma 1 1 minus the conditional variance with the notation sigma 1 1 dot 2 3 to p and divided by the usual variance sigma 1 1. This is coming from the fact that sigma 1 2 sigma 2 2 inverse sigma 2 1, this was nothing but sigma 1 1 minus sigma 1 1 dot 2 3 2 p. Why? If you recall that we had also seen with the conditional expectation, we had also seen the conditional variance of x1 given x2, and this was nothing but, this was my sigma 1 1 minus sigma 1 2 sigma 2 2 inverse sigma 1 2 with this notation. Right. So, because of this fact, what we have is the square of the multiple correlation coefficient is the unconditional variance of x1 minus the conditional variance of x1 conditioned on x2 divided by the unconditional variance. So, what we say is that the square of the correlation coefficient in the case of the multivariate normal distribution is giving me a interpretation like that it measures rho 1 2 3 dot p, the square of it measures the fraction of reduction in the variance, that is the unconditional variance of x1, that can be the reduction. This reduction, when can it be obtained? Well, when I condition this x1 on the given information of x2, that can be obtained by conditioning on x2. So, that is a new interpretation that we can give when we have some distributional assumption, namely the random vector follows a p-variate multivariate normal distribution with some covariance matrix or dispersion matrix, a sigma. Okay, so, this is one other interpretation, and of course, if you recall the bivariate normal distribution, so that we have x is now a two-dimensional random vector. So, let this be our fourth point to be noted, and this is, we have the bivariate normal case, x following a bivariate normal with the usual notation. Let us write mu 1 mu 2 sigma 1 square sigma 2 square and rho, the bivariate normal case. Now, here I have to consider a partition of x vector as x1 and x2, right. That is, in the case I am considering multiple correlation coefficient of x1 given x2. Now, it is basically a bivariate correlation coefficient type, and in sigma matrix we have to consider a partitioning of the type what? It is the usual sigma matrix. For the sigma 1 1 I have only variance of x1. So, it is sigma 1 square according to my notation, then it is covariance between x1 x2, that is rho sigma 1 sigma 2, and then here, well, the remaining part is again a one dimensional case. So, I have sigma 2 square. So, this is a situation. What is variance of x1 conditioned on x2? Well, it is, if I just go back to my earlier formula, it is nothing but sigma 1 1 sigma 1 2 sigma 2 2 inverse and sigma 1 2. Now, in this case, what is this? Sigma 1 1 is sigma 1 square, this is rho sigma 1 sigma 2 1 by sigma 2 square, and then again I have rho sigma 1 sigma 2. This is giving me sigma 1 square, and you have a rho square sigma 1 square. That is what we are looking for. This is sigma 1 square 1 minus rho square. If you recall, in our bivariate normal, if you recall, well, we have not done bivariate normal case separately, but then this is the conditional variance that we get in the case of bivariate normal, and recall that the expectation x1 given x2 is nothing but mu 1 plus rho sigma 1 by sigma 2 and x2 minus mu 2, right. So, that what is rho 1 dot 2 square? Well, again what we had seen earlier, that it is sigma 1 1 minus sigma 1 1 dot 2 3 to p by sigma 1 1. So, in this notation this is sigma 1 square minus this variance, the conditional variance, which is sigma 1 square 1 minus rho square, and then I have sigma 1 square. This is leading me to rho square, which is the square of the correlation between x1 and x2. So, the multiple correlation coefficient here is actually the bivariate correlation coefficient, the usual correlation coefficient between x1 and x2. So, that this is, I can simply write that the multiple correlation coefficient rho 1 dot 2 is nothing but the mod of the usual correlation coefficient, the square being equal to this square, and I can have, of course, this rho correlation coefficient, the usual correlation coefficient can lie between minus 1 and 1, but the multiple correlation coefficient is always between 0 and 1. So, this is the modulus of the usual correlation coefficient between x1 and x2. So, this is one way I can think about the bivariate normal case, and after this a very small point, that is, if you have, suppose till now we were considering a partition of the random vector where there was only one element in the first sub vector. So, now if we partition the random vector in a way so that I have a sub vector initially which is of dimension k, and the remaining how many p minus k coming in the next sub vector, right. So, that I have to talk about similarly partitioning the variance covariance matrix. So, this is now going to be partitioned in the form. So, the first element is no longer a scalar, it is again a matrix. So, let us call it sigma 1 1, it has to be of dimension k, because this is talking about the variance covariance matrix of all the k variables that are included in the first sub vector x1. And then I have sigma 1 2, which is talking about the covariance between the elements of this x1 and x2. So, that this has to have dimension k cross p minus k, the transpose of this matrix here. So, this is p minus k cross k, and lastly the variance covariance matrix of the p minus k random variables coming in x2. So, this is a square matrix of dimension p minus k. So, this is how I am partitioning the variance covariance matrix when the random vector is partitioned in this way. And then I can think of the multiple correlation coefficient between any one element of this x1 conditioned on the elements of the x2. So, let me say that let xi be a variable in the subvector x1. So, obviously, I can be any one of the k elements that are members of x1. So, I goes from 1 to k, and then I say the multiple correlation coefficient between xi and the elements of x2. So, let them be without loss of generality, let them be the last p minus k variables. So, that is k plus 1 up to p. We should write it xi with xk plus 1 to xp. So, that is up to xp is the notation is rho I dot k plus 1 up to p. Let me put a bigger dot for this, and this is nothing but sigma I transpose sigma 2 inverse sigma I by sigma I. So, obviously, we are talking about here the variance of xi, and this vector sigma I is nothing but the, we are talking about a particular row of this sigma 1 2 matrix. So, this is nothing but where the row where covariance between xi and the other variables, that is k plus 1 to p, these are considered. So, where xi, say if it is transpose, it is nothing but the ith row of, since we are saying it is ith row, so let us say it is of sigma 1 2. So, this is how I can simply give the multiple correlation coefficient when not necessarily the first subvector is a scalar, it can also be a random vector. Just like here we have partitioned it in this case, so that there are k variables in the first vector, and I consider any one of the elements from here and consider its multiple correlation coefficient with the members of the other subvector of the remaining variables. Okay. So, it is just a case of properly handling the covariance matrix and then considering which row you should take up from this covariance part, that is sigma 1 2. Rest of it remains same. We will have to consider sigma 2 2 inverse, and here also we will have to consider the scalar, which is the variance of that ith variable which we are considering. Okay. So, let us now talk about the sample correlation coefficient. If you have a random sample multivariate data, so that sample multiple correlation coefficient, how do we calculate it? So, that's, so now we have, what we have is a random sample of size n, say, of multivariate data. So, each of them be the same p variate random variables, and we have a sample of size n, x1, x2 to xn, and we are going to calculate the multiple correlation coefficient from the given data. So, what we do is we simply consider again the mean vector x bar, which is nothing but 1 by n. We consider the mean over the observations over the n observations, and for each of x1, and in this way we get the mean. So, to complete the mean vector, the sample mean vector, and similarly we also have the, this is the mean vector, and let us put the word sample in bracket, and sample covariance matrix, we have the notation S for this, and let our, this is actually 1 by n minus 1 with divisor n minus 1. So, that I have x j minus x bar, x j minus x bar, okay, j from 1 to n, and then we define some A matrix. Let A be this one with this divisor coming with S. So, that is n minus 1 S. So, that I simply consider this type of matrix sum of x j minus x bar, x j minus x bar transpose, and then I will partition, well, I consider the partitioning of S. So, that I write this is S11, S12, just like the way we had handled sigma, S12 and S22. Similarly, I can have a partitioning of A also, not a problem. So, I have here A11, say the vector A12 prime, A12 and the matrix A22. So, it is obvious that I am partitioning X into the form that I have one element here, say x1 again without loss of generality, and the remaining p minus 1 here, vector x2. So, that the S and the A matrices have been partitioned in this way, and then we can define sample correlation coefficient between x1 and x2 to xp. Note that these are again symbolic. This x1 can be any xi, and the only thing that will result is the absence of this xi from this p minus 1 remaining variables, right. So, this I will write as sample correlation coefficient between x1 and x2 to xp is nothing but our usual R1 to, now the sample notations. So, the Greek being replaced by the letter R, and we have this as A12 transpose A22 inverse A12 by A11 root. Note that if I write with the elements of the S matrix, then this does not change, and this is exactly because of the relationship between A and S. So, this is S12, S22 inverse S12, and then I have S11 raised to the power half, right. One thing can be noted from here that if x1 to, now we are always interested in knowing what is happening if these random variables are coming from the normal population. So, if this is a random sample from p variate normal distribution, normal p mu sigma, then this R 1.23p is the MLE, the maximum likelihood estimator of the population multiple correlation coefficient rho 1.23p, right. Now that we are talking of the sample correlation coefficient, we can actually think of devising tests on the population correlation coefficient rho 1.23p. So, for this we have to know something about the sampling distribution of this sample correlation coefficient or some function of this sample correlation coefficient. If you recall the usual bivariate case, you can think that you may recall that the testing procedure is devised on a function of the sample correlation coefficient R, and it is of the form R square by root of 1 minus R square with some constant, and this following a t distribution. So, let us see what is happening here, and if this generalization leads to the case of the test procedure on the simple correlation coefficient. Now, before we talk about the sampling distribution of this R or some function thereof, we have to talk about two very special type of distributions, the multivariate spherical distribution and the elliptical distribution. So, we first define what is the multivariate spherical distribution. The definition is of multivariate spherical distribution we say that a p dimensional random vector x is said to have a spherical distribution, obviously in this case a multivariate spherical distribution, if the distribution of x and hx, the distributions of x and hx are the same for all orthogonal, for all p by p. Obviously, we are considering a square matrix, this being p cross 1. So, we have for all p cross p orthogonal matrices, for all such type of orthogonal matrix H. Example, well, you can very easily think of one example, that is the multivariate normal distribution x following normal p with 0 say sigma square I, so that we have no problem of correlation, only the variances are present, and that to the homoscedastic case, so that the variances of each of x1, x2 to xp is sigma square. So that I have the sigma matrix reduced to a diagonal matrix sigma square I, and I say that X is following a normal with mean null vector and variance covariance matrix sigma square I. Now, if H is an orthogonal matrix, the distribution of Hx from our earlier results on multivariate, we know that this also has to be p-variate normal, right, with mean A mu. If you recall, what was the distribution of Ax when x is following multivariate normal? This is coming from that. So, this mean will be H mu, which is null, and sigma square H transpose H as the variance covariance matrix. Now, H being an orthogonal matrix is actually giving you back to sigma square, and this is IP in both cases obviously. So, we have this X particularly following this type of multivariate normal distribution. This is a case of a multivariate spherical distribution. Secondly, if you think of, so this is the first one, there is a distribution called a special type of distribution, E-contaminated normal distribution with PDF the type E times 2 pi sigma square to the power minus p by 2, and then I have the exponent term, that is 1 minus 1 by 2 sigma square x transpose x, and then comes a term like 1 minus E times 2 pi to the power minus p by 2, and the exponent term minus half x transpose x. Now, note that this part is actually coming from x following multivariate normal, the one we have talked about just now with mean 0 and dispersion matrix sigma I. Here this is even simpler. I have a case of multivariate normal from 0 I, and a combination of these with convex combination of this type, that is E with and 1 minus E multiplied with these PDFs, is giving me the PDF of the E-contaminated normal distribution, and this is also an example of a spherical distribution. Otherwise, we can also talk about one more. This is the multivariate T distribution with NDF, and it is having a PDF like gamma n plus p by 2 by gamma n by 2, and then we have n pi to the power p by 2 with 1 plus 1 by n x transpose x, actually okay, x transpose x with n plus p by 2. Well, p comes from the dimension of x, x is p cross 1, and if you have n equal to 1 here, n equal to 1 here gives the multivariate Cauchy distribution. Okay. So, these are the three examples that I am giving of multivariate spherical distribution. Next, we talk about the elliptical distribution and see the connection between the elliptical distribution and the spherical distribution, and we must not forget about the main connection, that is the connection of all these with the distribution of the multiple sample correlation coefficient, right. So, the definition of elliptical distribution is, we will say that x, a random vector, p-variate random vector x is follows elliptical distribution with parameters mu and say a V matrix. This is like the covariance matrix V, square matrix of dimension P, a positive definite, the notation we are using for positive definiteness. So, we say the random vector follows an elliptical distribution with parameters mu and V if its PDF is of the form Cp, let us write it in the next line, Cp determinant of V raised to the power minus half, and then we have a function of this type x minus mu transpose V inverse x minus mu, right. And the notation, the symbol that we say is x is following E P with parameters mu and V, right. And if, note that if x follows E P with mu replaced by the null vector and I P V replaced by the identity matrix, so it is sort of standard elliptical distribution, mu being replaced by null vector and sigma replaced V replaced by I P, then in this case x has a spherical distribution Second point is that if y is coming from a p-variate spherical distribution, so if y satisfies the condition of spherical distribution, so this follows p-variate spherical distribution, and if we define a linear transformation like x, which is c times y plus mu, where c is p by p and non-singular, right. So, this also remains a p-dimensional vector x, and in that case x will follow an elliptical distribution of dimension p, c being p cross p with parameters mu and v, but where v is, it has to be in terms of c, it is actually c c transpose. So, we have defined multivariate spherical distribution and the elliptical distribution and shown the connection between the elliptical distribution and the spherical distribution. Now, we go back to our sample correlation coefficient and look into the distribution of not r but r square. Okay. So, we are now talking about, after having defined this, we talk about the distribution of r square. R square, let us write r for r1 to the sample multiple correlation coefficient. So, I am simply writing r for this. Again, this is symbolic, this can be sample multiple correlation coefficient between any member of x1, x2 to xp and the remaining. Okay. So, distribution of r square is, we talk of, let y augmented with x1, then we have the sample. So, that is y1 to x1 and we have yn augmented with xn be a random sample of size n, right. So, let us denote the n dimensional vector yn as y1, y2 to yn, the n observations of the random variable y, and let X, the observations on X be arranged in a matrix form. So, let this X transpose be a P minus 1 cross n dimensional matrix, which means basically these are all one dimensional 1 cross 1 and these are all P minus 1 cross 1 dimensional vectors. Right. So, these elements can be arranged in the way x1 to xn. These are the columns of this matrix, each of these having P minus 1 dimension, right. And then we will see that if y has some distribution, then it will lead to some distribution of the square of the sample correlation coefficient, and in the case of multivariate normal distribution of y, what can be the distribution of the sample correlation coefficient. Okay, so now we are considering the distribution of R square with our background of the definition of spherical distribution and elliptical distribution. So, now we have said that from a random sample of this type of size n, we are considering arranging the observations. So, we have the vector y and the matrix X transpose, where we have incorporated our full data, and then we say that suppose y is a random vector having a spherical distribution with the probability of this is equal to the null vector being 0, and let X be independent of y and is of rank. Now, if I say that if R is the sample correlation coefficient it's between y and x1, x2 to xn. So, this is now denoted by I have R square as A12 transpose with A22 inverse, then I have A12, A11 as we have noted earlier with A matrix. How do I form this A matrix? Now that I have actually the random vector is, say it's of some form z, and how does this z look like? Well, I have y1 to yn, let this be the first part, the one variable which has been separated out, and then I have x1 to xn. These are p minus 1 dimensional, so that together we have a p dimensional case. But now we are using different notation of variables, y for the one dimensional case coming in the first part, and then the p minus 1 coming in the lower part, which are being denoted by x1 to x1, x2, etc. Okay, so this A matrix is the sample variance covariance matrix along with the divisor. How can we express it in terms of y and x? Well, it is nothing but I have it as z with in minus 1 by n 1 transpose. These are vectors of 1, and this is z transpose, where z is defined in this way. So, this is our z, right. And then this is the sample correlation coefficient I have, and this R square has beta distribution with parameters half of p minus 1 and half of n minus p. That is the data dimensionality including y and this p minus 1 dimensional vectors x and half n minus p n being the sample size or the number of observations on the random variable. That is, if this is so, by our well known result we have n minus p by p minus 1 times r square by 1 minus r square is following an F distribution with degrees of freedom p minus 1 and n minus p. So, now when we talk about the distribution of the sample correlation coefficient or square of it or some function of this, we have to have some distributional assumption in the background, and we saw that we are forming a case like y. The partitioning of the random vector is in this form where we have the random variable y and the random variables x1 to xp minus 1 giving in total a p-variate random vector, and if we have some assumption on the distribution of y, if we say that it follows a spherical distribution, actually the y vector which includes all the observations on y, y1 to yn, that follows a spherical distribution, then only we can have a distribution of this type where r is coming into the picture in this form, r square by 1 minus r square times n minus p by p minus 1 is a very well known F distribution with degrees of freedom p minus 1 and n minus p. And if we have the additional assumption that in particular if the combined random vector, that is if y1 x1 to yn xn, each of them they are independent, if y these are independent normal p-variate normal, because this is one dimensional, this is p minus 1 dimensional, these are independent normal p mu sigma, then when the population correlation coefficient, when the population multiple correlation coefficient rho, actually we can write here in the form rho y x1 to x p minus 1, or simple the population coefficient rho 1 to rho p, our usual notation, so that these are now 2 to p instead of 1 to p minus 1. So, this is equal to 0. When this is true, we have n minus p by p minus 1 r square 1 minus r square follows a F distribution with this degrees of freedom. So, this fact can be very well used for the purpose of testing of this multiple population correlation coefficient being equal to 0 when the observations are assumed to be coming from the multivariate normal distribution. What we will do is we will simply say that we have a test statistic of this form following the F distribution under H naught. So, this can be very well used in the testing of inference for the multiple correlation coefficient. So, when we are saying that this is known to us, then for testing H naught, that rho 1 or the notation that we are using now y x1 to xp minus 1 is equal to 0 against the alternative H a, that this is greater than 0 because it is lying between 0 and 1. So, this is greater than 0. So, we can use test statistic n minus p. Have you written capital? Well, it is no need to write the capital N here, it is the small n, the sample size. What about earlier case? Similar mistake we have made here. So, this is simply small n, right. And we have this following. Okay, so we use this test statistic n minus p, p minus 1, r square, 1 minus r square, following f p minus 1 n minus p under h naught. So the test procedure is simply reject h naught at 100 alpha percent level of significance if the observed, we need to calculate the sample multiple correlation coefficient and then this factor, if the observed test statistic, that is n minus p, p minus 1, r square, 1 minus r square is greater than f of p minus 1 n minus p at alpha, where f alpha p minus 1 n minus p is the upper alpha percent cutoff point of f distribution with degrees of freedom p minus 1 and n minus p. And recall that if p is equal to 2, we have the usual bivariate case, and what is the statistic in that case? The test statistic reduces to n minus 2 and this is r square. Well, let us write r, no problem, we can write r square for this also, r square by 1 minus r square. This is going to follow an f distribution with f1 and n minus 2 under h naught, and this is equivalent to saying that the root of this, that is r root n minus 2, so let us write this, r is equal to correlation coefficient between y and x. Now there is no question of x1, x2 to xp minus 1. So this is a two-dimensional case and we have r root n minus 2 by 1 minus root 1 minus r square following a t with n minus 2 degrees of freedom under h naught, which is the population correlation coefficient is equal to 0. Again, this is the usual bivariate correlation coefficient between x and y and x here. Okay, so we get back the case where when we consider p equal to 2 in this general form for p is any number, so that this the generalization works nicely here and we get back the usual two-dimensional case for p equal to 2. Okay. So after this we have only one thing to be considered, but note one factor, we have not actually derived the distribution of this thing r square by 1 minus r square etc., or the beta distribution that we are talking about. That is what we have is r square has the beta distribution with parameters p minus 1 by 2 and n minus p by 2. This derivation that coming from the assumption of spherical distribution of y is extremely cumbersome. So we avoid the derivation. What we have done is we have only defined what is spherical distribution and what is elliptical distribution, the connection with the sample distribution of sample correlation coefficient, but this is without proof to be noted, right. So this is without proof. So this derivation has not actually been done, we are only mentioning it here, it is this, and after this comes quite easily. If we have, this is from simple knowledge of sampling distribution, if we have beta distribution, then we can have this type of thing as an f distribution. And the fact that helps us in the testing of hypothesis of the population correlation coefficient is the situation where we use a distributional assumption of a multivariate normal of y and x, the joint distribution of this as a p-variate multivariate normal. So, as we were saying that the distribution that of R square is a better distribution with these parameters p minus 1 by 2 and n minus p by 2. This we have accepted without actually deriving. So, this has gone without proof, and after that this is a simple knowledge of sampling distribution, that if R square follows beta distribution with these parameters, we will have this type of function of R square following an F distribution. However, for the purpose of testing of hypothesis on the multiple correlation coefficient, we are making the distributional assumption that the combined distribution of yx1 to yn xn, this is a p-variate normal distribution with mean mu and variance covariance matrix sigma, and then if we have the null hypothesis that this is in fact equal to 0 against, we are testing this hypothesis against that this is greater than 0, we can very easily use this test statistic which will follow an F distribution under H naught, and so that the test procedure is a simple procedure based on the upper alpha % cutoff point of F distribution, of the relevant F distribution. Here after putting the value of p equal to 2, we can also easily establish the case of the bivariate case, where we have the sample correlation coefficient R is a simple correlation coefficient between y and x, and we see that if we put p equal to 2 here, we get back our t statistic, because n minus 2 R square by 1 minus R square, this is an F distribution with degrees of freedom 1 and n minus 2, which is equivalent to saying that the root of this, the square root of this term here is following a t distribution with degrees of freedom n minus 2. So, after this we have just one small point to be considered, which is the partial correlation coefficient. We will go very briefly with this. And we say that suppose we have x following the usual p-variate normal distribution with mean mu and variance covariance matrix sigma, and we partition x in the form, I have x1 having k elements, so this is k dimensional, and x2 which is p minus k dimensional. So, we have partitioned x in this way. Consequently, I have mu also partitioned in similar manner, mu 1 and mu 2, p minus k cross 1, sigma, the variance covariance matrix has been partitioned in the way sigma 1 1, sigma 1 2, sigma 2 1 and sigma 2 2. This is k cross k, this is p minus k cross p minus k, and coincidentally this will be of the relevant appropriate dimensions k by p minus k, p minus k by k. And then we have x1, the conditional distribution of x1 conditioned on x2. So, distribution of x1 given x2 is nothing but a k dimensional normal distribution, if you recall, with mean mu 1 plus sigma 1 2 sigma 2 2 inverse x2 minus mu 2, and the variance covariance matrix is sigma 1 1 minus sigma 1 2, sigma 2 2 inverse sigma 2 1, right. So, this we are denoting by sigma 1 1 dot 2. So, let sigma 1 1 dot 2 is sigma 1 1 minus sigma 1 2, sigma 2 1 inverse sigma 2 1, and we say that let sigma I j dot k plus 1 to p be the ijth element of sigma 1 1 dot 2. Then we can define the partial correlation coefficient between xg and xk, suppose xg and xk, which are components of the first subvector, which are components of x1, the partial correlation coefficient between these, which are components of x1, when x2 is held fixed, is denoted by rho gk, and then I have the elements of x2, that is k plus 1 to p, and is defined as the correlation between xg and xk in the conditional distribution of x1 given x2. That is, by the simple notation I can write rho of gk dot k plus 1 up to p by my notation of sigma ij, or whatever we had written, that sigma ij, the ijth element of sigma 1 1 dot 2, this is sigma gk k plus 1 to p, and we have in the denominator sigma gg k plus 1 up to p with sigma h k plus 1 up to p, this raised to the power half, because these are the variances. Okay. So, this is the definition of partial correlation coefficient, which has the interpretation that it is the correlation coefficient, the simple correlation coefficient between xg and xk, when the distribution that we are considering is the conditional distribution of x2 given xk. Note that xg and xk are both members of this subvector x1. So, we conclude our discussion on multiple correlation coefficient with a very little introduction about the partial correlation coefficient. With this, our next topic henceforth is going to be the principal component analysis.